So the paramagnetic system in NMR spectroscopy is a jargon for a system that contains an paired electron or several. So we have that electron and we have an ensemble of nuclei, and there are a few effects which are associated specifically with the presence of this electron. There are obviously relaxation effects and things we have covered in the relaxation theory lecture, but there are also magnetic susceptibility effects to do with the fact that in an applied magnetic field, this electron would acquire some non-zero equilibrium magnetization. That magnetization would affect the nearby spins through the magnetic field that it induces, but more importantly, this magnetization, because the electron usually has an isotropic G-factor, would depend on the orientation of the molecule, and if the molecule tumbles, would leave some complicated extra shielding effects on the nuclei. So the topic of today's lecture is precisely that. It is the extramagnetic shielding that is produced by the presence of an unpaired electron on the surrounding nuclei, and the name that it has in the trade is pseudocontact shift. And this is something that is of great utility in paramagnetic NMR spectroscopy. About a third of all proteins in nature are metalloproteins, and so you very often have calcium, magnesium, or another metal coordinated somewhere in the protein, and it is often possible to replace it with a lanthanide by just extracting the metal and putting another metal into the protein and take advantage of the associated effects. So what we'll do today is several things. First, we'll take a look at the general, I'll just remind you, the general theory of magnetizable systems. And then we will derive the expression for the electron susceptibility from quantum mechanics. And then we'll use the expression for the electron magnetic susceptibility to derive a simple expression for pseudocontact shift. So a big blast from the past, a lot of classical electromagnetism, a lot of statistical thermodynamics, and ultimately a bit of quantum mechanics that we will have to go through today. So, in a bulk substance, if we have just a cube of something extending to infinity in every direction, as you remember from your classical electromagnetism, the magnetization of the substance, the bulk volume magnetization of it, is a quantity called volume magnetic susceptibility times the quantity H naught, which is the original magnetic field. Yeah, we use B naught, which is the magnetic induction, but this is the magnetic field proper that's measured in amperes per meter, that we do not often encounter in magnetic resonance, but it is, of course, what defines the magnetization of the bulk substance. Now, if we look at very weak magnetic fields and weakly magnetizable substances, so long as the substance is not ferromagnetic, which is usually true in our systems, B naught, our magnetic induction, is approximately equal to mu naught H naught, and we can switch the notation to something that is more usual in magnetic resonance and take it from there. So this chi is volume susceptibility. And that is the magnetic field. And that's the induction in our usual units of Tesla. Now, in molecular quantum mechanics, it is not usually convenient to work with volume susceptibility because you fairly rarely consider a bulk substance. So we would need to switch here to molar and ultimately molecular susceptibility, and the molar susceptibility chi m is defined as you'd expect. It's the molar mass of the substance divided by the density of that substance times the volume susceptibility. So what was susceptibility per cubic meter becomes the susceptibility per mole of the substance. And then, well, the usual statistical thermodynamics would get us the equilibrium magnetization, We know that the energy of our spin in a magnetic field, if it is an electron, is the Bohr magneton times the electron G factor times the projection quantum number of that electron onto the field times the field itself. And then if we would like to know our equilibrium magnetization, average from statistical thermodynamics, I would remind you that if we want some average property A, then what we do need to have is a sum over AI, so the value of that A in the ith energy level, then X minus EI over KT divided by the partition function. So the sum over I X minus EI over KT. So that's the standard expression for the equilibrium value of some observable in statistical thermodynamics. So why don't we take the same expression and adapt it for the magnetization? We know that we have multiple energy levels in the spin, so we will sum over the projection quantum numbers ms from minus s to s, so all energy levels of spin s. The magnetization is mu b, the Bohr magneton, times GE times the projection quantum number in that state, times the exponential of the energy, and we take the expression for the energy from here, so X minus GE mu B ms B naught over KT. And in the denominator, we would have the partition function that is merely the sum over these exponentials. So the sum, again over ms from minus s to s, x minus GE mu B and s B naught over KT. Now, as you know, our interactions in magnetic resonance are very weak. In particular, they are usually much smaller than KT. This is still the case in moderate magnetic fields in EPR spectroscopy. And so we can approximate our exponential in the usual way, that an exp of minus a small number is approximately equal to 1 minus that small number plus something that of the order of that small number squared. And we assume that our interactions are so weak compared to KT that it is permissible to just ignore this second order correction, in which case these two get replaced by 1 minus what appears as an exponential. So that becomes approximately equal to sum over ms mu b g e and s, and then 1 minus GE B S B naught over QT divided by sum over ms of 1 minus GE B ms B naught over KT. Now, a little bit of mathematics later. What we simply need is to calculate the corresponding sums. This is not a calculus class, so I'll just skip the corresponding trivial algebraic transformations. What we arrive at is the following: minus GE squared mu B squared B naught over 3KT S plus 1. So it's useful to take a look at what this is. So we have calculated the equilibrium magnetization of the substance based on the energy level argument and statistical thermodynamics. It depends on the temperature in an inverse fashion. So the lower the temperature, the greater the equilibrium magnetization would be. Some things that we take full advantage of in DNP, for example, when we freeze the sample to acquire the biggest possible electron magnetization. It depends on the G factor squared. So the larger the G factor, the better it is. And it depends on the square of the total spin quantum number. So for things like gadolinium at low temperatures, the equilibrium magnetization would be quite large. There are other complications, of course, in systems with spin breakers and a half, but there goes. That's the expression. Now, on the other hand, we know from classical arguments that the same magnetic moment must be related to the susceptibility in the following way. Mu is chi m, the molar susceptibility, B naught over mu naught and Avogadro. And so when we equate this to this, the magnetic field cancels, as you can see. It doesn't depend, at least within the assumptions that we have made, on the magnetic field. A few other things cancel, but importantly, we do get a quantum mechanical expression for the molar susceptibility of our paramagnetic particle. Which, after we do the mathematics, becomes chi m equal to mu naught g e squared mu b squared and Avogadro 3kt s plus 1. That is the expression that we derived for a particular value of the electron G factor, or rather for the value that we have in the direction of the applied magnetic field. In the case when we do have an anisotropic G tensor, the same identical argument would apply for each eigenvalue of the G tensor, and so what we would get in the most general case is the A-th eigenvalue of the magnetic susceptibility tensor would be mu naught G A squared mu B squared over 3k T S plus 1, and I've removed an Avogadro to make it refer to an individual particle, and then AA is equal to XX, YY, or ZZ, the three principal values of the corresponding tensors. And so that is it. Now, if we know the G tensor for the electron, which we can easily measure using EPR spectroscopy, what we can immediately get is the corresponding magnetic susceptibility tensor. So, what shall we do with it? I will go back to this picture here. Imagine that we placed our system in a magnetic field. The electron acquired its magnetization. That has generated an extra magnetic field at the point of the nucleus, which has either partially compensated or partially enhanced the applied magnetic field. In the former case, it will be perceived by the NMR instrument as an extra shielding, because it resists the applied magnetic field. In the latter case, it will be perceived by the instrument as extra de-shielding, because the effective magnetic field became stronger. So let us now go through the corresponding mathematics and actually formulate the presence of this effect as an additional chemical shift, which would be dependent on the properties of this electron. It would obviously be dependent on the distance of this electron, and as we actually see in a moment, also the angles that this makes with the various anisotropic interactions. But ultimately, in liquid phase, assuming certain properties of this chi, we will see that the phenomenon behaves as an additional chemical shift, which makes it quite easy to measure and, as we shall see in a moment, quite useful. Right, so from what we've got so far, here we can conclude that the magnetic moment acquired by our electron, mu e, I will now just drop the label m, just refer to that as the susceptibility, is our chi, the susceptibility tensor, times the applied magnetic field vector, V naught, divided by mu naught. So that's the magnetic moment, so average magnetic moment of the electron. Now this magnetic moment would create a magnetic field of its own, and we know from classical electromagnetic field theory what that magnetic field is. It's just a field of a dipole. We go to Wikipedia, we take a look at the expression, we write it here. So the field created by this dipole, we'll call it V1, would be mu0 over 4 pi, the usual prefactor, then 3R Kronecker product of R transpose, and I'll explain what's it is in a moment, over R to the fifth, minus 1 over R cubed, scalar product mu E. Now, you all remember, hopefully, the expression for the dipolar interaction, and I've used here a shorthand. I've taken a vector, and I've taken a Kronecker product with the transpose of that vector. What this crocodile is the following. We have a vector, x, y, z, which is multiplied by the transpose of that vector, x, y, z. What this sign means is the Kronecker product. That means every element of this matrix should be multiplied by every element of that matrix, and the result stacked up. And so what we would have here is this times this, x, x, this times that, x, y, this times this, x, z, y, x, y, 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 z, z, x, z, y, z, z. So it's a shorthand of writing, shorthand way of writing what's called in the jargon a dyadic matrix. It's a matrix that is produced by such a transformation. And of course, then if we take 3 times this minus 1, you would get the usual dipole tensor. Yes, 3xx minus r squared, and so on. So this is just a shorthand way of writing these things. And it is, in fact, the preferred way, because as soon as we start taking derivatives with respect to that or transforming it, you find after a bit of practice that this is, in fact, considerably more convenient than storing explicit expressions for what the matrices are, because once you had written the matrix down, the structure of what had led to it has actually been lost. And that structure is quite valuable because it simplifies the transformation. Right. So, what we now have is our magnetized electron with this magnetic moment. We now have the magnetic fields that this electron has created at the nucleus point. So let us now calculate the additional energies that that interaction generates for the nucleus. We know, again from classical electromagnetic theory, that energy is minus mu n, which is the magnetic moment of the nucleus, transposed, because it enters a scalar product, times B1. Well, B1 we also know, so that becomes, after we substitute it in, minus 1 over 4 pi, then mu n, vector transpose, 3r cron r transpose over r to the fifth, minus 1 over r cubed times chi times b0. And what I've done is I've substituted in place of that the expression here. I've put in mu n. Mu0 that was here has cancelled with the mu0 that was there, and so what we ultimately have is this. And you see, it has a structure of a scalar product. We have a vector transposed here. We have some matrix product in here. So this matrix times this matrix, the separability tensor matrix, times the magnetic field vector. So it is actually the structure of a Dirac bracket. If you remember that from quantum mechanics, even though here the argument up to this point is in fact very significantly classical. So this is the energy of our nucleus that it has acquired due to its interaction with the electron that has been magnetized by the applied magnetic field. So what we now need to do is we need to extract the corresponding chemical shift. Now, this is where the treatment that you would see on this board is significantly different from the treatment that you would see in common textbooks. Courtesy, in fact, of us using this vector form. Prior to the arrival of quantum chemistry, which was, I think, about maybe 25 years ago, when the calculation of chemical shielding started being routinely done using quantum chemistry methods, we would have to go into long hand-waving argument as to how these things behave for various directions of the applied magnetic field and for various directions of the nuclear dipole and things like that. Quantum chemists, however, have done us a great service in defining the chemical shielding, sigma, as the derivative of the total molecular energy with respect to the nuclear magnetic moment and with respect to the applied magnetic field. And this is a vector derivative, and I think one of them is transpose, this one. And at this point, I also need to explain to you what they mean by taking a derivative of a scalar with respect to a vector. So if I have df, which is a scalar function of a vector argument, and I take a derivative of it with respect to that vector argument, the result is this. It's df by dx1, df by dx2, and so on. So it is a vector of derivatives with respect to the components of this vector. Similarly, if I take derivative with respect to the transpose of a vector, I would have a transpose vector here filled with derivatives with respect to the components of it. And so what we've got here is we have a first derivative with respect to the magnetic field vector, which makes this a vector quantity. And then we have the second derivative with respect to the transpose, which goes into the same argument as here. And so a second derivative with respect to a vector and its transpose is in fact a matrix. And this we will see now. If I take this expression here, you see mu n occurs linearly. It's multiplied into. And so if I take the derivative with respect to it, what happens is it simply vanishes from here. If I take a derivative with respect to the magnetic field, it also occurs linearly in here, so it just disappears from here. And so the result that I would get is actually a matrix, as we've discussed, and as it should be there. Now, unlike quantum chemists, we are not actually interested in the chemical shielding. We are interested in the chemical shift, which is a constant minus the shielding. Constant we can ignore because spectrometer has a limited reference point, but that does mean that we do have a minus here in front, which we have to keep track of. And so after taking the derivative, this minus disappears, this disappears, this disappears, and so what we've got is 1 over 4 pi 3r cron r transpose over r to the fifth minus 1 over r cubed. And that is the chemical shift tensor that is generated by the presence of that electron, which is assumed to be sitting at the origin, at the point where our nucleus is sitting, which is R. Now, the last thing that we need to do here before we get a reasonably final expression for this is to note that in liquid phase we don't actually observe or even need the full shift tensor. What we need is its isotropic part, and the isotropic part of sigma, known as sigma PCS, pseudocontact shift, is 1/3 of its trace, and that's the isotropic component of any matrix that is rotational invariant. And so what we have in the end is 1 over 12 pi then trace of 3r cron r transpose over r to the fifth minus 1 over r cubed times the susceptibility tensor, and that's it. So this is the textbook expression for the pseudocontact shift that is generated by the presence of the electron with the magnetic susceptibility chi. In practice, what happens is when we are fitting the data, we measure off these chemical shifts from, for example, an HSQC experiment. What it would look like is if we take our NMR spectrum, where the metal is something diamagnetic, calcium, magnesium, some diamagnetic lanthanide, lanthan, we would have a number of peaks in the HSQC. It's usually the HN HSQC. Then we repeat the same experiment, but we substitute lanthanum with terbium, for example, which is paramagnetic, and we observe the changes in these chemical shifts. They will move around the picture. And so what we would have is the observed values for these sigmas. What is then done is the least squares fitting to try and extract, on the one hand, the susceptibility tensor. It can be measured, but it can be computed from the G tensor as well. And what is valuable about this is it provides distance restraints for the molecular structure. We know what the pseudocontact shift is for each atom, and then we can, when we run the molecular dynamics, we can impose these values as structural restraints on the molecule to make sure that any candidate structure that we have actually obeys the experimentally observed pseudocontact shifts. And that's the primary use of this property in structural biology. They are used as distance and angle restraints when we are refining the structures of paramagnetic proteins. Right, so this is perhaps the most general expression for the point case. You would notice that we did use the point dipole expression here. And so this formula here would actually break in the vicinity of a distributed paramagnetic center because the point dipole approximation doesn't apply. But further than about 5 angstroms away from that electron, it's actually a pretty good approximation. And in practice, we can see these pseudocontact shifts experimentally out to about 30 or 40 angstroms. So it is a significant amount of distance restraints that this is generating, which are practically actually quite useful. Now, what we need to do, though, is to do some further transformations on this to derive the form that's actually commonly used in biochemistry, because if you open structural biology papers that are using pseudocontact shifts, their programmers are probably using this expression under the bonnet anyway, but biologists aren't particularly friendly with, expressions like that. And so we can actually use spherical coordinates to derive something here that uses a rather simpler grade of mathematics than the ones that we had used in deriving these expressions. So let me wipe the board and do that piece. Any questions so far? Yeah, so if you ever do liquid state paramagnetic systems, you'll see this. Okay, so let us start with this expression here, and let us transform the picture and the system into the basis which diagonalizes the magnetic susceptibility tensor. So we would assume that this is a diagonal matrix with 3 elements, chi xx, chi yy, and chi zz. And so our sigma PCS from there would be 1 over 12 pi trace of 3 x, y, z, cron x, y, z over r to the fifth minus 1 over r cubed. That's the dipole chi. So we will now open this up in the matrix form. So I will actually use this explicit expression in place of these. I would take r to the fifth out of the bracket here and pull the 3 into the matrix. And so what we get then is 1 over 12 pi trace 1 over r to the fifth. And then we have a matrix. And if chi is diagonal, it simply multiplies the diagonal components of this matrix. And so what we've got is 3x squared minus r squared in the 1, 1 element, then 3y squared minus r squared in the 2, 2, then 3z squared minus r squared in the 3, 3. And because we're about to take the trace, we don't really care what else is in there, so I'll just put the dots. And they should be multiplied by the corresponding elements of the susceptibility matrix, so chi xx times chi yy times chi zz. And now the trace of this is the sum of the diagonal of the matrix. And so we get a somewhat easier expression as a result, which is 1 over 12 pi 1 over r to the fifth of 3x squared minus r squared chi xx plus 3y squared minus r squared chi yy plus 3z squared minus r squared chi zz. There is one interesting thing about it. You would notice that if we have an isotropic susceptibility tensor, this expression vanishes. If chi xx is the same as chi yy and the same as chi zz, we can take chi's out of the bracket in here. We would have 3x squared plus 3y squared plus 3z squared, which is 3r squared, minus r squared minus r squared minus r squared. It would disappear. It would go to 0. So pseudocontact shift, even though it is an isotropic quantity, is only non-zero if the electromagnetic susceptibility is anisotropic. So if you encounter an electron somewhere in a highly symmetric environment with isotropic G tensor, do not expect pseudocontact shift from it, because there's none to be had. It specifically needs to be something in a non-symmetric coordination environment which does have an isotropic G tensor, and then the phenomenon comes out. What this also suggests to us is that this doesn't depend on the isotropic part of chi, because any isotropic part will just cancel itself out. And so if we define the quantities which are more directly related to the anisotropy, so I will define a property of delta chi x, the axiality of that tensor, that would be chi zz minus chi xx plus chi yy over 2, or alternatively, that's 3/4 of chi zz minus chi isotropic, and the rambicity of the corresponding tensor, which is the difference between the xx and the yy, minus chi yy, then this expression simplifies a little bit more. So we can observe, by just doing bracket reordering in here, that this is 1 over 8 pi r cubed chi zz minus chi iso times 2z squared minus x squared minus y squared over r squared plus delta chi rambicity x squared minus y squared over r squared. And finally, those of you who have been doing those things for a while would immediately recognize spherical harmonics. in here our usual second rank spherical harmonics that we should not be surprised by, because ultimately the nature of this interaction is dipolar. And so the same mathematics that comes about in the dipolar interaction should come about here. And we would also notice that this is in fact axiality. And so after we substitute the expressions for spherical harmonics, cancel all the numbers, all the pi's, and so on, all the normalization coefficients, we obtain the final expression for the pseudocontact shift that is used in most biology textbooks. It's 1 over 12 pi r cubed delta chi axial 3 cosine squared theta minus 1 plus 3 halves delta chi rhombic sine squared theta cosine 2 phi. So y20 spherical harmonic and a linear combination of spherical harmonics with other projection numbers in here. So again, if the interaction is isotropic, then it vanishes. If it is anisotropic, then these coefficients are non-zero. And this form assumes that we are working in the eigenframe of the electromagnetic susceptibility tensor. If you look at the pictures that this produces, if we have an electron that is positioned somewhere in a protein, let's assume that our susceptibility tensor is axial, in which case we would have a y20 spherical harmonic in here. You know what it looks like. It has positive lobes and a negative belt. And so there will be nuclei around that center, positioned here and here, that would experience the reduction in the chemical shift, so they will be shielded to a greater extent due to the presence of the unpaired electron. And there will be nuclei around here which experience an increase in chemical shift, so they will be de-shielded by the presence of that electron. And what is important, that as is also the case with many other dipolar phenomena, the distance dependence of the effect is 1 over r cubed, so it gets weaker with the distance. A few dozen angstroms is typically the limit at which it can realistically be observed. So that's about it with the pseudo-contact shift. The rest is out there in the papers. If you're working in solid state, as I think in DNP spectroscopy you almost inevitably would these days, you would encounter the full anisotropic version of that. It will also manifest itself in the relaxation theory expressions. If you are working in liquids, as most biologists do these days, you would be exposed to the isotropic part of that, which depends on the reciprocal cube of the distance. Much nicer than over Hauser effect, which as you know is 1 over r6, and also stronger because we have an electron in the system. And this is what the picture is going to look like, and it will provide you the distance restraints for molecular structure determination. There are a few caveats here, which I didn't mention. They are in a way for the more professional people who work with this directly. There are certain constraints on relaxation time of the electrons involved, because here we have quite liberally taken the average with respect to the orientations, not mentioning that perhaps in some cases either the relaxation is sufficiently slow or the tumbling sufficiently fast, so that the electron doesn't have the time to adapt its quantum state to the fact that the molecule has rotated. So implicit here is the assumption that the electron relaxes instantaneously to the new state, which is reached by rotating a molecule and therefore shifting around the anisotropic G tensor. But for commonly encountered lanthanides, that is in fact the case, and so we don't need to worry. But we do need to worry in the case of nitroxide spin labels, for example, where that might not necessarily be the case. Okay, that's as much as I have to say on the subject of chemical shift from paramagnetic centers. Any questions?